All right, kiddos, let's talk about how the mass of a particle relates to its speed or its velocity. It turns out that all particles, regardless of their mass, have the same kinetic energy. What does that mean? All particles, regardless of mass, have the same kinetic energy. Well, let me try to relay that to you by giving you sort of a strange analogy. Is it possible for this monster truck here, which probably weighs several tons, to have the same kinetic energy as this little toy truck? Most people would say no. The monster truck has a ton of kinetic energy. It's huge. And that toy truck has hardly any kinetic energy at all. In fact, you could hit me with this monster truck and man, you'd squish me flat. You could hit me with that toy truck and it might annoy me. You might get my attention, but it really by no means is going to injure me. Well, that's not necessarily true. What if this little toy truck were moving very, very fast? What if I were to get it going hundreds and hundreds of miles per hour and moving through the air, and then you were standing in the way? Could it then quite possibly have the same energy as that monster truck? Yeah, it could do quite a bit of damage. The thing is, kinetic energy has a component of not only mass, but also velocity. So when I asked you if the toy truck and the monster truck could have the same kinetic energy, you said no because you assumed something. You assumed they were traveling at the same velocity. But I didn't say anything about their velocities, did I? No. So if I can get this toy truck to get moving very, very fast, can't it compensate for its lack of mass and have enough kinetic energy to do as much damage as the monster truck? Yes, it can. Now, molecules, particles, atoms and molecules have that same property. Read this sentence again that I started at the beginning of the video. All particles, regardless of mass, have the same kinetic energy. What does that tell you about light molecules compared to heavier molecules? Think about that for a second. Let's go to the next page, where I make the same statement over again. The average kinetic energy of all molecules are the same at a given temperature. The velocities of different kinds of gases are different because they have different molecular masses. So instead of thinking about monster trucks and toy trucks, let's talk about molecules. Which type of molecule would move faster at a particular temperature? Light molecules like hydrogen or heavy molecules like sulfur hexafluoride? Let's see, hydrogen has a molecular weight. Let's see, it has one proton. Each of them has one. So its atomic mass is 2 atomic mass units. Sulfur hexafluoride is quite a bit bigger. Sulfur alone has an atomic mass of a little bit more than 32 atomic mass units. Fluorine, there are 6 of them. Each one has a molecular or an atomic mass of 19 atomic mass units, which we'd multiply by 6. So we would have, let's see, 19 times 6 plus 32. It would have a molecular weight of 146 atomic mass units, quite a bit larger than hydrogen gas. So, which type of molecules would move faster at a given temperature? Well, if hydrogen and sulfur hexafluoride have the same kinetic energy, what does hydrogen have to be doing in order for it to have the same kinetic energy as sulfur hexafluoride? That's right. Hydrogen has to be moving faster. So there's a video you're going to watch that's on Google Classroom for you. And what I do is I actually inhale some sulfur hexafluoride for you, which remember has an atomic mass, molecular weight, 75 times bigger than hydrogen gas. And you'll see the difference that it makes as far as its velocity is concerned as I speak after inhaling this. It has quite the dramatic effect. So that video will be posted in Google Classroom for you to watch. All right, one other thing I want to mention in this rather short video is diffusion. So diffusion is the movement of gas particles from high to low concentrations. It always goes from high concentration to low. So the movement of gas particles from a high area of high concentration to low concentration. So think, if you would, if I had a bottle of perfume. I'm going to try to draw my best bottle of perfume. Does that look like a bottle of perfume? Put a little design on it. And I took the lid off. So the lid is now off. Does that look like a lid? Now some of that liquid in there will evaporate and turn into the gaseous phase, won't it? Well, those gas particles are going to move from an area of high gas concentration to an area of low gas concentration. So if you were sitting across the room from me, eventually you would smell the odor of those perfume molecules. That's called diffusion, the movement of a gas from high gas concentration to low. Now keep in mind, remember, lighter gas molecules move faster than heavier, don't they? So we could say that light molecules diffuse faster than heavier molecules. So if you had some hydrogen and some sulfur hexafluoride, and let's just pretend they both had different odors for a moment, wouldn't you, and they were across the room from each other, or from you, wouldn't you smell, and once again, if it had an odor, wouldn't you be able to detect the hydrogen gas before you'd be able to detect the sulfur hexafluoride gas? Yes, because these two molecules, sulfur hexafluoride and hydrogen gas, have the same kinetic energy, but the lighter one has to be moving faster so it can have the same kinetic energy as the big heavy one. Got it? All right, next video we'll be talking about change of state. So solid to liquid to gas, or maybe even solid to gas directly. So stay tuned.